Hello and welcome to part 4 of this week's lecture. In this lecture, we are going to look at different devices that we can use for pressure measurement. In the previous lectures, we talk about hydrostatic pressure, that is how the pressure increases linearly as you go deeper into the liquid. And in this lecture, we are going to use this concept for pressure measurement. So one of the simplest methods or devices to use for pressure measurement is what we call Mercury Barometer. And this is a device that is in use since early 1600s, and that is one of the reasons why atmospheric pressure is also known as barometric pressure, because that was one of the first measurements that was done to measure atmospheric pressure. So it is actually consists of a glass tube that is filled with mercury, and then it is turned upside down into a beaker that is filled with mercury as well. And then you have a small void here that is mostly vacuum, or you have a very low vapor pressure of mercury. Okay, so we can write the expression for the pressure, that is PB minus PA. So PB is the pressure due to the atmosphere acting at point B, minus the pressure that is inside this void or inside this tube, that is PA, equal to rho GH. And we, as I said, that the vapor pressure of mercury is really low at room temperature, so we can almost neglect it, and we get the final expression that the atmospheric pressure at point B is equal to rho GH. Now from this equation, by feeding these different values, we can calculate what is the atmospheric pressure. So for the case of mercury, the density is 13,560 kilograms per cubic meter, and then we have the height that we can easily measure using a ruler, for example. So that is 760 millimeter, and we can convert it into SI unit. So if you feed these values in this equation here, you get the final value of atmospheric pressure, that is 101 kilopascal, and this is an absolute pressure. It is not a gauge pressure, and that is why we are using the absolute here to represent that. We can convert this pressure value into different units or into different systems of units. We have pound per square inch absolute, we have millimeter of mercury, we have meters of water. So we can use these conversion factors to convert this value from one system to another. So another kind of set of devices that we can use to measure pressure is what we call manometers. And a manometer is a device that uses a liquid to measure the pressure difference. So normally the pressure difference is relative to the atmosphere. So the simplest form of manometer, that is known as piezometric column or piezometric tube, is a vertical tube that is open to atmosphere at one end, and then it is attached to the system where you want to measure pressure, for example a pipeline or a vessel. And so if you want to measure the pressure at point A, we can write from hydrostatics again that pressure at point A should be equal to the pressure that is applied on the top of this tube, that is P naught, the atmospheric pressure, plus rho GH1, that is the pressure due to the height of this column here. And if we want to write it in the form of gauge pressure, we can take this P from this side to this side, and we have the gauge pressure, that is PA minus P naught, equal to rho GH. So just by calibrating this pressure with height, because we know the values of this rho and G, they are constant. So just by looking at the value of height, we can calculate what is the pressure difference or the pressure inside this system. Okay. So the piezometric tubes are commonly used in devices with low pressures, because obviously we don't want this liquid to go out from the top side, or we don't want to have very large tube that is not practical. So these are mostly used for low pressures. and they are very cheap. One of the limitations of this piezometer is that it can be only used for liquids, because if you use it for gases, the gas can just escape to the atmosphere. Also, these tubes are used for positive gauge pressures. It means pressures above atmosphere. And the reason, because if you have a vacuum in this system here, the gas can actually penetrate from the atmosphere through the liquid to the system. Okay. So to avoid these problems, we use so the piezometer, you will see this piezometer in your lab and also in some other engineering applications. So for example, here you have this device called orifice meter that we use to measure the velocity of the fluid, and then it gives you the pressure drop at this point. Similarly, we can use these piezometers again, another method of measuring velocity of fluid, and that is due to the contraction, the pressure changes, and by measuring this pressure using this piezometer, you can evaluate the velocity of the fluid inside this pipe. So to avoid the limitations of piezometer, we use another device that is called U-tube monometer. And this U-tube monometer can be used for gases and for negative pressures. And what it is a kind of a U-tube that is shown here, and it's a different kind of U-tube that you normally watch videos on. And so in this U-tube, you have this pink fluid. So this pink fluid is called gauge fluid. So this is a fluid that we normally know the density and its properties. Okay. And most of the cases it's actually mercury. So we can, by using this U-tube monometer, we can calculate the pressure difference at point A and the atmosphere. Okay, so if we again try to write this expression of pressure difference, again we can start it from point A, and if you see that here you have a fluid that is a gray fluid of density ρ1, for example. And we can write the expression at point 2. The pressure will be P2 should be equal to PA, that is the pressure of this system here. And then we have the pressure due to the hydrostatics, that is ρ1 GH1, that is the height of this fluid here. Okay. And we can also write that the pressure at point 2 should be equal to pressure at point 3, and that we know from isotropy of pressure that we discussed in the beginning of this week's lectures. And what it means that if a point of pressure is at the same height, we can actually jump from one point to the other point if the height is the same. Okay. Another way of looking at is that why these pressures are same at these 2 points is that if you go down, for example, you will see that the pressure will increase due to the height or the depth of this fluid, and then you go in this direction, and then if you go up, you will see that the pressure will decrease again. So this increase and decrease in pressure cancels out, and that is why the pressure at this point should be equal to the pressure at this point that is at the same height. So we can just jump across from this point to this point. So we can write P2 is equal to P3, and then similarly we can develop an expressions for point 3, that is if we look at from this side now, so we have the pressure P naught that is acting on the liquid here, that is P naught, and then we have the pressure due to hydrostatics that is equal to ρ2 GH2, that is the height of this liquid here. And we can equate equation 1 and equation 3, and we can write the expression here that is that just equate the two pressure terms here. And we can write the expression for PA minus P naught, that is the gauge pressure inside your system here, and that gives us that is equal to ρ2 GH2 minus ρ1 GH1. Okay, so that is the pressure difference that you will get for the system. So let's say if instead of liquid here you have actually a gas in this gray area, And we know that the density of gas is way smaller, or almost 3 order of magnitude smaller than the liquid. So we can actually cancel this or neglect this term here, and then we can just write that Pa minus P node is equal to rho 2 GH2. Okay, so that is for the case if you have when you are using this U-tube manometer for a system with a gas in the system. So we can increase the range of the pressure measurement, and if you again look at this relation here, so one way of doing it is to increase the H or increase the density or both. In most of the cases we use the denser liquid, that is the mercury, so it means that we cannot really play with the density of the fluid that much, but we can increase the height of this tube to measure the pressures or high pressures. Okay. So another form of manometer that we normally use to measure sensitive pressures is what we called inclined manometer. So inclined manometer actually is a U-tube manometer, and this U-tube section actually is stretched, and so that you can actually measure smaller pressure differences, for example. So this fluid here, for example, in the picture, there are 3 fluids here. We have fluid 1, that is, let's say, a liquid of density rho 1. Then we have the gauge fluid that is of density rho 2. And then we have the third fluid that is density rho 3. And then we have this inclination angle that is theta, obviously. So the theta angle controls the sensitivity of this instrument. Okay. So this equipment or this device is mostly used for small pressure differences or sensitive when you need a sensitive pressure measurement. So that's what we use this inclined manometer. Again, if we do the pressure analysis and we try to find what is the pressure difference Pa minus Pb, that is the pressure at this point minus the pressure at this point. Okay. So again, let's work from point A to point B. So at point A, again at point here, from point A to point 1, we have this pressure, and that is equal to Pa, the pressure at in this vessel or in this pipe, plus the pressure due to hydrostatics due to this height h1, so that we can write Pa plus P rho 1 GH1. Okay, so that is the pressure at point 1. Similarly, if we go down, we can go from point 1 to point here. We can just jump because again these points are at same height. So we can assume that the pressure at point 1 should be equal to pressure here at this point. Okay. So to calculate the pressure at point 2, we just need to use this length or this length of the gauge fluid. So we have, because we are going up, it means that we are we are going to decrease the pressure. As you know from hydrostatics, when we go deep, the pressure increases, but as you go in the upward direction, the pressure should decrease. And that is why we are using the negative sign here. So the pressure at point 2 would be equal to rho 2 G L2 sine theta, because this is the L is a diagonal length, and then if you convert it into height, that is this height here, that will be L2 sine theta. Okay, so that gives us the pressure P2. So that will be the total pressure, that will be the pressure at point 1 plus the pressure due to this length L2. Okay. And then we have the final bit, we have the pressure at point B that we can write. Again, we are going up, it means the pressure is negative or pressure is becoming lower. So we can write it as P rho 3 GH3. Okay. And this all should be equal to the pressure at point B. Okay. We can rearrange this equation, and you can check my algebra for here, that if you can write PA minus PB, that is, you take the PB on this side, and then you have minus rho 1 GH1 plus rho 2 GL2 sine theta plus rho 3 GH3. Okay. So this is the expression that gives you the pressure difference between point A and point B. Okay. And now if we have, for example, if we have gases, we have gas in pipe A and we have gas in point B. So we can, and that is actually one of the common situations in industry. You can have, for example, air here, you have another kind of gas here. So that is a relevant case in industry. So in case of gases in these 2 points, we can actually write that for the gases at point A and B, rho 1 should be equal to rho 3 because gases have similar densities, but these densities are way lower than the density of the liquid, okay, especially if you have mercury in this gauge as a gauge fluid. So for the case of gases, this equation will simplify as PA minus PB equal to rho 2 GL2 sine theta. Okay, so this is the equation that you will use. Sorry, there is no 3 here. So this is the equation that you will use to measure the pressure difference between 2 points. Okay. Another example of a device that is very commonly used in industry is what we called Borden gauge. And Borden gauge just works more or less on the principle of this whistle blower that we normally use in parties. For example, when you apply pressure, the tube moves, and it's kind of a representative of the pressure you are applying here. Okay, just to show you a video how this pressure gauge works. So you have this tube that is connected to this dial, and as you exert pressure, the curvature of this tube change, and then the dial on this scale moves to show you the pressure equivalent that you are applying through the fluid. Okay, so the moving end of the tube rotates a hand on the dial through a linkage system, as I showed you in the video. Okay, devices can be used for gauge pressures and also can be used for vacuum pressures. The only thing is that then you have to graduate them in millimeters or inches of mercury to show the negative pressure. Okay. So these are this is the example of actual device. For example, that is how it looks originally, and then if you open it, you can see the assembly of it. You have this elliptical tube, and that is connected through a linkage system to a dial system. And if you increase or if you stretch out this tube, the dial will move on the scale. Okay, and only one pressure gauge was harmed in making of this slide. So in addition to pressure gauges that we discussed that use the concept of hydrostatics, there are other forms of pressure devices that are also used in industry, and one of the most commonly used devices is what we call a pressure transducer. So a transducer is a device that transfers one form of energy, for example, the mechanical energy in the form of pressure, to another form of energy, that is electrical energy, for example. So Borden gauge, for example, transfers pressure to displacement of this elliptical tube. So in industry, we use mostly electrical pressure transducers. It means that the electrical pressure transducer converts the displacement of a diaphragm to an electrical signal. So here you have the system where the diaphragm is connected to the system or a vessel with the fluid. And as this fluid exerts pressure on this diaphragm moves or shows deflection, and that deflection is converted into electrical signal. Okay, and this is how it looks. This device looks like. So this is the port where the fluid exerts the pressure, and this is the diaphragm where you receives this pressure and show a form of deflection, and then the remaining parts here just convert that deflection in diaphragm into an electrical signal. Okay, so these are how they look like. Just literally you can see they look like nuts and bolts, but they can actually convert the pressure into electrical signal. And this is a form of pressure transducer that we normally use to measure the pressure that is submerged. For example, in tanks, we can leave it there and the fluid enters here, and then the inside of this pressure transducer looks like this, and then we get the pressure reading through this electrical signal on our computer. So that is all for the topic of pressure measurements. And now you should be able to define pressures, calculate hydrostatic pressures, and compare different methods of pressure measurement. And in the coming lecture, we will look at fluid flows. Thank you for your time.